All right, so suppose you have two vectors like this, and we've seen, lots and lots of applications where you've got like one or two vectors acting on an object, offset by an angle and so on. Now, suppose you visualize this vector A casting a shadow on vector B, right? If you like, suppose I were to shine a flashlight like this on vector A, but holding the flashlight perpendicular to B, right? Just like this. Can you envision that there's going to be a shadow of A onto B, right? There's going to be a shadow of A onto B. Now, just like if I were to shine a flashlight here, it's going to cast the table is going to cast a shadow on the floor. Now, if it's perpendicular, right, there's going to be a certain length to that shadow. We call the shadow the projection of A onto B, right? So that's the terminology, the projection of A onto B. Now, that projection, depending on how the angles work, right? Because this is at an angle and we're shining the light 90 degrees perpendicular to B, that projection is not going to be the same height, the same length as vector A. Okay? Does that make sense? Now, when we take the length of that projection, so just the length, that's a scalar, just a number. When we take the length of that projection and when we multiply it with the length of vector B, what we get is something called the dot product. So the dot product, all right, is the product of the magnitude of the projection and the magnitude of vector B. All right, so we're just multiplying two lengths by each other. The length of the shadow projection times the length of vector B. Conceptually, are we okay with what we're doing? Okay? All right. Now, how do we practically find the dot product? Well, first of all, the dot product is written like this. A dot B, just like this, and that's how it's read. It's A dot B. All right? And it's it's a raised bolded dot like the multiplication dot, but like a little bit more bold. And so suppose you have two vectors, A1 and A2, and B1 and B2. The way in which you find the dot product is A dot B is A1 B1 A2 B2. So you just multiply A1 B1 A2 B2. Now, let's explore this a little bit. All right? Here we have a right triangle. Is there a way to relate the sides of this right triangle? How are the sides of the right triangle related to each other? A squared plus B squared equals C squared, right? Okay. So let's take a look at this for a minute. So suppose I wanted to find the length of BA, right? If I wanted to find the length of BA, what could I do? Distance formula. That's the square root of, what is it? It's A1 minus B1 squared plus A2 minus B2 squared, right? Just distance formula. Is that right? Okay. So now if I square both sides, then I get BA squared is equal to A1 minus B1 squared plus A2 minus B2 squared. Now, we also said, right? All right, so let's do this. Let's square them first. Let's distribute the square here. So it'll be A1 squared minus 2A1B1 plus B1 squared plus A2 squared minus 2a2b2 plus b2 squared. Yeah, Claudia?
So do those two?
Take a look here. Since we're talking about magnitudes, right? Is there a way that we could find the magnitude of vector A? What's the magnitude of vector A? These are its components. So is it a1 squared plus a2 squared? Right? And then what's the magnitude of vector B then? Same thing. Okay, but with the B's. So now let's go back and see what we have here. I have the magnitude of BA squared equal to, take a look at what I have here. A1 squared plus A2 squared. What is that? That's the magnitude of A squared, right? And then I have B1 squared and B2 squared. What is that? Magnitude of B squared. Now, what's the Pythagorean theorem tell us about these three? What's the Pythagorean theorem tell us? BA squared is equal to what? The magnitude of A squared plus the magnitude of B squared, right? So now what is this? That's what we get from the Pythagorean theorem, right? But take a look. Take a look. When I was looking for the magnitude of BA, I have this plus I have some extra stuff. Is that right? So take a look now. The Pythagorean theorem says that BA squared has to equal A squared plus B squared. But then when I was trying to find the length of BA another way, I have all this other extra stuff. How can it be that you try to find the length of a segment two different ways and you get two different answers? That can't be. A segment only has one length. Like there is no arguing back and forth, right? Well, what is all that then? All of this extra stuff, okay? This is negative 2 A1 B1 plus A2 B2, right? This is the dot product. This is the dot product. This is the remnant, okay, of A and B. So if A and B were not at 90 degrees, right? And if they were curved a little bit, okay, like if it had like a different angle, then we would have had to adjust this, right? Is everything okay? Yeah. So A squared and B squared are equal to BA squared only if these two are right angles. If these two meet at right angles, right? If this was an obtuse angle, would BA be less than or greater than this? Greater than. How much greater? That much greater. Okay? If the angles were less than 90 degrees, would the length of BA be less than or greater than what we got? It's less than. How much less than? This much less than. So now, if they're 90 degrees then, how much should all of that equal to? Zero. Okay? So that's the meaning of the dot product. That's one way to see the dot product. Yeah.
Which angle are you talking about?
The angle between A and B. You see this 90-degree angle?
Yeah, so if it's 90, why do we have the dot?
That's the thing. If it's 90, this is going to be 0.
Okay.
You see that? If this angle here between A and B was greater, the length of BA would be this plus a little bit more. This much more, as a matter of fact. Or if it was going to be less, it would have been that much less. So that's the dot product. Okay? Yeah.
How come you disregard the negative 2?
Because it's a factor of, right? So if A1, B1 plus A2, B2 is 0, then 2 times 0 is still 0.
Right.
You see what I mean?
But if that has a value, then would you multiply that
Yeah.
by 2?
Yeah.
But it doesn't say that.
The 2 just comes out of the formula. It's the same as, like in the law of cosines, It's a squared plus b squared minus 2ab cosine theta. Oh my gosh, it's all coming together. Well, okay, hang on. I don't want to get ahead of myself. We're there. We're there. You don't think so, but we're there. Okay, so now, so that's the dot product then. Okay, yes.
Just for terminology's sake, if that angle is greater than 90, the dot product is over 1. It's greater than that.
Yeah. Okay, so now, what we saw above, right there, were orthogonal vectors. Ortho, what's the word ortho, the Greek word? What is it? Orthodontist. What does the orthodontist do? What does he do to your teeth? He straightens them, or she straightens them. What does an orthopedic surgeon do? They straighten your bones. So ortho has this meaning of straight. Orthogonal, you have, it means perpendicular, right? Vertical and horizontal. So if the angle between two vectors is 90 degrees, so the dot product is going to be 0. Why? If we talk about the dot product still as a projection or a shadow, now if the angle between the two vectors is 90, and if I still hold a flashlight on top of this green vector, how much of a shadow is it going to cast? 0. All right? There's not going to be any shadow. Like if I hold a flashlight straight above a desk, there's not going to be a shadow underneath unless I angle it, right? So same thing here. If two of them are perpendicular, then the dot product is 0 because there is no shadow cast onto B. There is no length of a shadow. It's just a point which has no length, okay? So in the case of orthogonal vectors, the dot product is always 0. And that's how you know that the vectors are orthogonal and vice versa. All right, so let's go to this next example just to find the dot product, right? So U dot V is equal to, we multiply the first, so negative 3 times 3 plus 4 times 6. So that's going to be negative 9 plus 24. What do we think? 15. All right? And the dot product is a scalar. The dot product is a scalar number. All right. This is something new when it comes to vectors. Okay? So far, we've just had to deal with real numbers most of the time. What happens when you add two real numbers, what do you get? Another real number. When you multiply two real numbers, you get another real number. When you add two vectors, you get a vector. But when you take a dot product of two vectors, you don't get a vector, you get a scalar. Okay? All right. Now, what about U dot V here? It's negative 28 plus 28, 0. So those two are orthogonal. Well, I mean, both. Just know that it equals 0 means it's orthogonal. Okay, so here are some properties of dot products. Properties follow the commutative. Vectors are commutative. Yes, question?
So, is the dot product the shadow, or are we not talking about
The dot product is the length of the projection, the shadow, times the vector on which it's being projected. So it's the length of the projection times the length of vector B. Okay? There is a product. Like there is an actual product. Yes.
So if it's 0, the angle is 90.
Yes.
So like
They're perpendicular.
But aren't they, I don't know.
So if you were to graph, 2, 7 and negative 14, 4 and measure the angle in between, it would be 90. Okay? Yeah. We could do it later. We're going to do a couple things later on. All right. Distributive property, right? The dot product also follows the distributive property, scalar multiplication property, and so on. This is an important one. If you multiply, the dot product between 0 and a vector is 0, because 0 can't cast a shadow on anything, so it's just 0, right? Now, if you take a dot product of a vector with itself, so u dot u, right? What are you doing? If it's u dot u, suppose u is like 4 and 2. If you do u dot u, what is it that you're doing? 4 times 4 plus 2 times 2. What is that? What have you found? You're squaring them, but then what have you found? What is this? It's the magnitude of this, right? It's the distance of it's the magnitude of that vector. What's the magnitude of vector u? What's the magnitude of vector u? The square root of what? 4 squared plus 2 squared, right? And what did we do when we did u dot u? 4 squared plus 2 squared. Let's do it again in this next example.
So is this just like finding the magnitude of the result?
Right. Look, here is vector A. Take a look here, and you'll see what I mean. Take a look here. What is the magnitude of vector A? What's the how would you find the magnitude of a vector? It's the square root of 36 plus 25, right? Right? Okay, which is the square root of 61. Fine. Now, let's find the dot product. So let's do A dot A. That's going to be A dot A. Right? What is that? Negative 6 times negative 6, 36. 5 times 5 plus 25. So what's A dot A? It's 61, which is the square of the magnitude. Do you see that? So A dot A is just the magnitude squared. Right? Look, they're the same. Okay? Why is that? Let's talk about why that is. Here is why. If I have a vector A, and if I have the clone of that vector A, okay? If I were to shine my light now, here, perpendicular, how much of that A will be cast on the other A? All of it. So if the dot product is the product of the length of the shadow times the length of the vector, then it's the length of A times the length of A. It's the square of the magnitude. Okay? So conceptually it works. Which means when two vectors are perpendicular, what's the dot product? 0. That's the minimum. When is the dot product maximized? When they're totally parallel. When it's the same vector parallel to another, right?
It's maximized when it's parallel?
Yeah.
And it's never going to get more than like that number squared.
It can't. How can it? Right? Because the shadow, like, there is no way to make that bigger.
So, yeah.
You'll see later why it can't. In fact, that's what we're going to talk about now, is the angle between the two vectors. All right? Okay. So, yeah. So let's talk about the angle between the two vectors. All right? And with this, we could come up with a more concrete definition. All right? And you'll see how, like, so many things are connected to this. All right. So this is the projection of A onto B, right? That length right here. All right? Now, and we said that this is perpendicular to B. So now I have a line here, the red line, and then another one perpendicular to that. So that's a 90-degree angle right here, and an angle theta. All of a sudden, I have a right triangle with a theta, and I could use my trig functions, right? So if I'm talking about this red projection and the blue vector A, which one of the trig function would that be? Cosine, right? So that would mean that cosine of theta is equal to A No, I'm sorry. Thank you. It's the projection of A onto B over A, right? So what does that mean? It's the projection of B onto A. Oh, sorry. It's A onto B. It's this way. Okay? So now, what does that mean? If A dot B, right, is the length of the projection times the magnitude of B, okay, then A dot B is equal to, take a look here. How much is the projection? If I solve that formula for the projection, it's what times what? It's A times cosine theta, right? So it's the length of the projection, which is A cosine theta times magnitude of B. Okay? That means A dot B is equal to, if you just write it, neater, A times B cosine of theta. Yes, A dot B is a dot product. Conceptually, it's the length of the projection times the length of vector B, right?
But that doesn't play out into the form.
I'm deriving it. I'm deriving. So what is the length of the projection? Well, I got it from here, right? Times that. Okay, so now let's go back. So since we're dealing with a cosine, what's the maximum that a cosine could be? 1. So now, going back here, right? Going back here. If it's the magnitude of A times the magnitude of B times the cosine, then this is the most it could be. You see that, Jesse? If we're talking about this, if it's the length of this times the length of this times the cosine, which the most it could be is a 1, then the highest it could be is the magnitude of these squared. You see that? Isn't that cool?
Could be lower now?
Yeah. It could go, right? Cosine goes from what to what? -1 to 1. -1 to 1. So that's it all connects. I'm telling you, man, there's like a math heaven out there and it's all connected. So now, I can take this formula in the box and can I solve it for cosine of theta? Divide, right? So it's A dot B over magnitude of A, magnitude of B, and take a look here. That's what we have over there. So that's how you find the angle between two vectors. Okay? So now, let's find the angle between these two vectors. All right?
Wait, I'm kind of confused. So
While I answer this question, take a few minutes and find the angle between these two vectors. Go. I'm not going to let you have all the fun. I'm going to do it too. So cosine of theta is equal to u dot v over magnitude of u, magnitude of v. So now we do these in components. So u dot v is equal to 1 times 2 plus -4 times 6. And that's 2 minus, so that's 22, right? -22. Is that right? Okay, now, magnitude of u is the square root of 1 plus 16, 17. Magnitude of v is the square root of 4 plus 36, root 40. If that was going to be your final answer, yes, you would have to simplify the root, but we're going to plug it all into the calculator, so don't waste time. So cosine of theta is going to be -22 over the square root of -17 times 40. See how I did that? Okay. Why is it -17? Somebody. 17 times 40. All right. So what is the angle then in between these two? Inverse cosine. What's the angle? Sounds good to me. Well, does it sound good? I don't know. I'm not sure about that. Let's see if it does sound good. Look at vector u. It's 1 and negative 4, right? 1 and negative 4. Huh? And what's vector v? It's 2 comma 6. Right there. Is it reasonable that the angle between them is 147.5? That's pretty reasonable. Okay, that's an easy way to check your answer. All right? Okay. Now, before I move on here, okay, before I move on there, I'm going to go back to the first page of this lesson. Okay? And the reason why I'm going to do that is because I'm going to show you guys something. Okay? Let's go back. Oh my gosh, I'm like, oh my gosh, I'm bracing myself because this is so exciting. I'll come back to that page. So take a look at what I said here. I said that BA, let's just write it like this. BA squared is equal to A squared plus B squared minus 2 A1 B1 plus A2 B2. Correct? Now, BA squared is equal to A squared plus B squared. I'm not changing anything. Minus 2 times. We said this was the dot product. Isn't that what we said? What did we just say the dot product is equal to? A, B, cosine theta. Is that right? Guess what this is, guys? Guess what this is? Not math heaven. It is math heaven, but why is it math heaven? No, it's not B squared. It's magnitude of B cosine theta. What is it? It's the law of cosines, guys. This is the law of cosines. C squared is equal to A squared plus B squared minus 2AB cosine of theta. There you have it. Oh my God. Tell me that's not cool. How could I not get excited over this?
I think I'm going to remember the law of cosine from now on.
Thank you so much. Right? This is going to go down in the books, guys. This day is going to go down in the books. Right? There we go. So this is why now. So this is it now. This is why we use this for the lengths of triangles that are not 90 degrees. Because if it was 90 degrees, it's A squared plus B squared plus C squared. But now we have an adjustment. We either have to add a factor or subtract a factor. And this is where the factor comes from. Do you see that? Do you see how they're all connected? Do you now see why it's so beautiful? This is why when I'm teaching the law of cosines, I'm so excited because I know that this is where it comes from. You see that? Because it's deeper, huh?
You have a secret that you
I know, all this time. Ever since geometry. See, this was like, it's catharsis. Oh.
I can see it. On cloud nine.
Okay. Oh, you haven't seen anything yet. So look at what's coming. Huh? No, that's not that exciting. Well, I guess it is, but not like this. Okay. So the projection of A onto B. Okay? Let's now take a really good look at that projection. Okay. The projection we said was the length of that shadow we're calling. So it's just the length. It's a scalar. It's 5. It's 7. It's 4. Okay? In the world of vectors, it's really, when you're just a scalar, you're really a second-class citizen. Now, to make something a vector, you have to not just have a magnitude, but also a direction. So how do we give that projection a direction, right? We just have 5. So now All right, the projection of this vector onto this is 5. Okay, but in what direction? Like, is it pointing that way, that way, that way? What is it pointing? Well, along which vector is that projection? It's along vector what? It's along vector B. So this projection has the same direction as vector B, right? Now, what gives us just direction without magnitude? What kind of vector? What kind of tiny little vector just gives us direction and not, what is it? The unit vector. So now, check this out. If I were to get the unit vector of B, tack it along to the length of this red segment, then not only is that a magnitude, but it also has a direction the same as B. Okay, so that's what we're going to do now. What we're going to do is we're going to take this. Remember how we just said this is the projection, right? It's A dot B over B from here, right? Okay. So now we're going to take this is the magnitude of the projection. We're going to take this and we have to multiply it by this stuff, the unit vector of B. Huh? Is it making sense? We have to multiply it by the unit vector of B. Hall pass.
Yeah.
Okay. So now take a look at what we just did. This was the magnitude of the projection. Okay? This was the magnitude of the projection. This is the unit vector. All right? So now take a look at what I have. On the denominator, I have magnitude of B, magnitude of B. It's magnitude of B squared. So it's A dot B over magnitude of B squared times vector B.
So what does this exact formula give you? Direction.
This gives you the full projection. So this is the full projection vector with magnitude and direction. Okay? So now, let's find the projection of this onto V. Okay?
So is the projection on the top of the page, is that incorrect?
No, that was just the magnitude. Now this is the magnitude and the direction. All right, so the projection of U onto V is going to be U dot V over V squared times the, not the magnitude, but the vector V. Yeah, I'm going to show you now. So first let's do U dot V. It's going to be negative 4 plus 30, 24, right? 26. And then we're going to do magnitude of V. It's the square root of 16 plus 36, 52. And just leave it that way because we're going to square it, right? So this is going to be U dot V, which is 26, over the magnitude of V squared, which is 52, times vector V. So this is 1/2, 4, 6, 2, 3. Oops, 2, 3.
So essentially for the magnitude of V squared, it's just going to be the number inside the root without the square.
Yeah, because you square it, right?
Yeah.
Yeah. All right, so this is the projection then of U onto V. Now, we're going to do something here. All right, so we have vector U and V. This new vector, I'm just going to give it a name, W, just so it's easier for me to refer to it. So W is the projection, and it's 2, 3, right? Okay, so now take a look at what we're going to do. Here, I'm going to draw vector U. And let's draw vector u in blue. Right, so vector u, we go down negative, we go left -1 and then up 5. So that's right there. Is that right? Right, so that's vector u. And now vector v is 4, 6. Let's do it with this one in green. 4, 6. So we're going to go over 4. 1, 2, 3, 4, and then up 6. Ooh. Right? That's vector v. Okay, now, what was w? W was the projection of u onto v, and it's 2, 3. So let's do that here. 2, 3. 2, 3. There we go. You see that? Yeah. So that's the projection. You see how it lies along that one, right? Because we gave it that same direction. So this is W. Okay? So what is this? This is the projection. If you're to look at it, at a 90-degree angle to V, that's how much shadow would be cast on there. Do you see that? It's perfect. So now we're not even done now. Take a look at what we're going to do now. Now it says to write u as a sum of two orthogonal vectors, one of which is the projection of u onto v. We just called that w, right? That's what we just called it. So we want u to be equal to w plus this new vector z. All right, some other vector, because it says to write u as the sum of two vectors, one of which is w, so w plus another one. Yeah. So now take a look at this. So u, what was u? It was -1, 5 is equal to 2, 3 plus z. So how are we going to find z? We're just going to subtract. So how much is z going to equal to? -1 minus 2, which is -3 and 2. So that's z. It's -3, 2. So take a look here. So z is -3, 2. And I'm going to choose a different color for z. Let's see. I like the orange. Let's choose orange for z. So look, z is going to go from, it's at -3, 2. -3, 1, 2, 3, 2 right there. All right, that's z, right? Not only are they perpendicular, not only are z and w, and not only are they perpendicular, take a look. Where did this come from? W plus z is equal to u. Is that right? So take a look. W plus z is equal to u. They're components. They add up to u. Do you see that now?
Before technology, this wasn't as cool.
Well, yeah. This is definitely pretty cool.
What is the red?
That's the W. Do you see that now? And the angle here, 90 degrees. So if I were to take all of that and tilt it over so that W lies on the x-axis, or if I were to tilt it over so that W lies on the y-axis, you could even imagine Z is going to be totally horizontal. You see that?
Is that the resultant vector of the shadow?
No. W is the shadow.
Yeah.
Oh, is
W is the projection. It could be.
Wow.
Yeah.
Is there a resultant vector?
The resultant. So U becomes the resultant between Z and W. Okay, why do we care about this? Why do we care about the fact that if you have vector U Okay, so now look, you have vector u, right? And it's one of its components lies along vector v. Why do I care about that? Because when you're exerting a force on an object in order to move it, if there is work being done, in order for work to be done, first of all, there has to be motion. If nothing is moving, you could be pushing as hard as you want against the wall. If nothing is moving, there is no work, even though you're exhausting all of your energy. So in order for work to be done, there has to be motion. Not only that, there has to be the force applied and the motion have to lie along the same direction. All right? That's the only time work is being done. So if you're holding something up, so like if the force is being pointed upwards, but something is moving in another direction, not in the same direction as the force, there is no work being done. So you see now that if I have a force vector, so suppose there is an object here that I'm trying to move, okay? If I have a force vector, it's the component of the force that's in the direction of motion that's going to make the difference. So if the object is moving that way, right? If I break down the force into horizontal and vertical components, it's only the vertical component of the force that's contributing to how much work I do. Okay? That's why a dot product. So when you when you learn this stuff in science in like middle school, you know, they teach you that work is equal to force times distance. Okay? It's hard for me to write it like this because in reality, work is force dot distance. Okay? Because when you put it that way, then it's the component of the force that lies along the same direction as the motion that contributes to the work. Okay? All right. So here, a person pushes a box with a constant force of 40 newtons at a constant angle of 45 degrees. Okay? And this should say find the work done in joules to move the box 12 meters. Okay, so well, okay, so here's what we're going to do. Okay, so force is 40 cosine 45, right? And how much? Negative 40 sine 45. Is that right? Because the vertical component is downwards. The distance, if it's moving 12 meters, then it's 12, 0. So now, look, if I do F dot D, look at how it all works out in the formula, right? If you do F dot D, then it's going to be 40 cosine 45 times 12 minus 40 sine 45 times 0. So do you see that it already cancels out? The way the dot product is, it already by itself automatically cancels out the component which is not in the same direction, which is perpendicular to it. Okay? So how much is that? 40 times 12 cosine of 45, Josh? How much? 339? All right, so let's say it's 339. And how did we get here? We multiplied force times distance. Force was in newtons, distance was in meters. So the work is 339.4. Newton times meter is a joule. Okay?
You pretty much just do like work equals like force cosine theta just like times the distance.
Right. It's FD cosine theta. So another way, and we're going to do this when we're doing our word problems. So work is force times distance. And what is A dot B? It's force times distance cosine theta, right? It's AB cosine theta. Magnitude of A, magnitude of B, cosine theta. Okay? All right. So this is the homework that goes with this lesson. And then in the next class, I just have like a whole bunch of word problems that we're going to do. And then I have a whole homework set on word problems. So we're going to spend at least 2 classes just on word problems. And of course, those are going to be included in your test as well before you leave for the junior trip.